Exoplanet implications. The planetary anomalies we've explored in our own cosmic backyard cast a profound shadow over our exoplanet discoveries. While scientists have identified thousands of worlds within their star's habitable zones, Venus teaches us that a planet's position alone reveals only a fraction of the habitability story. The rest might hinge on factors we can barely detect from afar. Astronomers increasingly recognize that rotation rates and magnetic fields serve as critical indicators when evaluating an exoplanet's potential to harbor life. A planet's spin directly influences how heat distributes across its surface, determining whether temperatures can remain stable enough to maintain. Liquid water, the universal solvent that enables life as we know it. Fast rotation, like Earth's, creates moderate day-night temperature differences and drives weather systems that distribute heat from equator to poles. Meanwhile, a robust magnetic field serves as a planetary shield, deflecting charged particles from stellar winds that would otherwise strip away atmospheres molecule by molecule. Unfortunately, these crucial habitability factors remain largely invisible to our current detection methods. When astronomers announce the discovery of an Earth-like exoplanet, they're typically referring only to its mass, radius, and orbital distance, properties we can measure relatively easily. The underlying assumption often goes unstated, that these worlds rotate and generate magnetic fields similar to Earth. But Venus and Mercury stand as stark reminders that such assumptions can lead us astray. What if the secrets of Venus hold the key to identifying truly habitable exoplanets among the thousands we've discovered? Consider the challenges of detecting an exoplanet's rotation. At distances measured in light years, discerning a planet's spin requires extraordinary observational precision, similar to trying to detect the subtle wobble of a spinning top from across a football stadium. Current techniques attempt to capture brightness variations as different surface features rotate into view, but this demands both exceptional light-gathering power and remarkable stability from our telescopes. Alternatively, scientists analyze spectral lines for Doppler shifts that reveal rotation speeds, measuring how light stretches or compresses as different parts of the planet move toward or away from us. These methods remain at the edge of our technological capabilities, working only for the largest, brightest exoplanets under ideal conditions. The James Webb Space Telescope represents our best hope for characterizing exoplanet rotation in the near future. Its unprecedented sensitivity and spectroscopic capabilities might finally allow astronomers to detect the subtle signals of planetary rotation, particularly for larger worlds orbiting nearby stars. Until then, our picture of exoplanet habitability remains incomplete, with rotation rates largely confined to theoretical models rather than observational certainty. Detecting exoplanetary magnetic fields presents an even greater challenge. On Earth, our magnetic field arises from the movement of molten iron in our planet's outer core, a dynamic system powered partly by our planet's rotation. This magnetic dynamo generates a protective bubble that shields our atmosphere from the solar wind. Without it, Earth might look much more like Mars or Venus, with its atmosphere severely depleted by constant bombardment from charged particles. Future missions may detect exoplanet magnetic fields indirectly by observing their interactions with stellar winds, similar to how aurora on Earth mark the collision between our magnetosphere and particles from the Sun. Such observations would be revolutionary, allowing astronomers to distinguish between truly Earth-like worlds with robust magnetic protection and those that, like Venus, may have lost their atmospheres despite appearing otherwise habitable. The exoplanets we've discovered often fall into categories based on limited observational data. We speak of super-Earths, mini-Neptunes, and hot Jupiters as if these classifications tell us everything about these distant worlds. Yet Venus reminds us how misleading such categorizations can be. If an alien astronomer observed our solar system from across the galaxy, Venus might appear tantalizingly Earth-like in terms of size and mass. Only by detecting its aberrant rotation, missing magnetic field, and toxic atmosphere would they recognize its true nature. tidally locked exoplanets, especially common around red dwarf stars, provide a fascinating case study in how rotation affects habitability. These planets always present the same face to their host star, much like the moon does to Earth. One hemisphere experiences perpetual daylight, while the other remains in eternal night. Venus offers valuable insights for understanding these worlds. Its extraordinarily slow rotation creates conditions that parallel those on tidally locked planets. By studying Venus's atmospheric circulation patterns, scientists can better model potential climates on tidally locked exoplanets, including whether atmospheric circulation might moderate temperature extremes enough to permit habitability. Red dwarf stars host many of our most promising exoplanet candidates. Their small size makes planet detection easier, and their longevity offers ample time for life to potentially develop. However, planets in their habitable zones orbit so closely that tidal forces typically lock their rotation. The absence of a magnetic field compounds these challenges. Red dwarf stars produce frequent, powerful flares that would bombard nearby planets. With radiation, without magnetic protection similar to Earth's, these worlds would likely experience significant atmospheric erosion over time. Our quest to find truly Earth-like worlds must therefore extend beyond the traditional habitable zone concept. A more sophisticated approach would account for rotation rates, magnetic field presence, atmospheric composition, and numerous other factors that collectively determine a planet's true habitability potential. The planetary anomalies in our solar system are crucial calibration points for interpreting exoplanet observations and avoiding overly optimistic assessments of habitability. This perspective enriches our understanding of exoplanet diversity